Imagine you're trying to understand why a language model generates a politically biased response. You ask what caused this. Is it the prompt? The model's architecture? A specific word choice? Traditionally, causal analysis has focused on variables, like drug dosage affecting blood pressure. But in modern AI systems, the raw inputs are pixels, tokens, or embeddings, units that lack inherent meaning. How can we ask meaningful causal questions when the variables themselves aren't semantically interpretable? This is where a new framework emerges: causal effects at the level of events, not variables. In this video, we dive deep into a groundbreaking paper by Junhyung Park and Yuking Zhou from ETH Zurich, which redefines causality through a measure-theoretic lens, bringing clarity, precision, and semantic depth to causal reasoning in complex systems. Let's start with the core idea. Causality isn't just about variables, it's about events. In probability theory, independence starts with events. Two events A and B are independent if P A B equals P A P B. Only later do we generalize to sigma-algebras and random variables. The same logic applies here. We define causal effects first on events, then extend them to sigma-algebras, capturing causality at the right level of granularity. The foundation of this work is the causal space framework, a recent axiomatization of causality that unifies structural causal models, SCMs, and potential outcomes. A causal space is a quadruple, omega HPK, where omega is the sample space of all possible outcomes. H is a sigma algebra of measurable events. P is the observational measure, what we see in data. K is the causal mechanism, a family of transition kernels encoding how interventions change the world. Crucially, the space has a product structure. Omega equals T omega T, meaning each component, like a token in a language model or a pixel in an image, can be intervened on independently. Now let's define causal effect, not as a shift in expectations, but as a change in probability of an event under intervention. Hash binary causal effects, yes or no. The most basic definition. An outcome omega has an active U causal effect on event A if intervening on set U changes the probability of A. Specifically, if Ku omega A not equal to P A, then omega does have an active causal effect on A. If this holds for all omega B, then B has an active causal effect on A. This is fine-grained. Unlike traditional treatment effects that average over all units, here we can ask, does a specific prompt, a specific omega, cause a model to generate a politically progressive response? And crucially, no control group needed. We compare the interventional probability Ku omega A directly to the observational P A. The baseline is the real-world distribution, not some hypothetical control state. But what if the effect depends on context? For example, a prompt asking for a neutral tone only affects output if the rest of the prompt is political. That's where conditional causal effects come in. Conditional causal effects, context matters. We now ask, does omega have a causal effect on A, given that some other event G occurred? This requires care. Conditional probabilities only exist if P, G0 and P do U delta omega, G0. But beyond that, we define. Omega has no conditional causal effect on a given G if, for almost all omega, the conditional probability Pg, A equals the interventional conditional probability P do U delta omega, G, A. This is a direct generalization of the independence result. No conditional causal affect conditional independence under intervention. Let's illustrate with a real-world example. Running example, travel insurance. Suppose a traveler faces accident risks depending on trip danger, low, high, none, and chooses whether to buy insurance, yes, no. The cost is 30 CHF for insurance, and 1,000 CHF if an accident occurs. We define omega dan equals NLH, right arrow danger level. Omega ins equals Y, N right arrow insurance status. Omega pay equals 0, 30, 1,000 right arrow payment. The observational distribution P shows that accidents are rare. Only 0.625% of trips lead to 1,000 CHF payments. Now suppose we intervene, force the traveler to buy insurance omega ins Y. The causal kernel K ins Y tells us that after this intervention the probability of paying 1,000 CHF becomes 0, because insurance covers it. Similarly, if uninsured, that probability jumps to 1.5%. So both Y and N have active causal effects on the event A equals, pay equals 1,000. But now, condition on the danger level. If the trip has no danger, G equals dan equals N, then buying insurance has no effect, accidents are already impossible. But if the trip is high risk, H equals dan equals H, then buying insurance does reduce the chance of paying 1,000 CHF from 0.625% to 0%. This captures treatment effect heterogeneity, a core idea in causal inference, but now at the level of events, not variables. Post-intervention causal effects, what happens after? Now consider a deeper question. Once you've already intervened, does a second intervention still matter? This is the post-intervention causal effect. Definition. Omega has no active U causal effect on A after intervening on HV if, for all omega V backslash U. KUV, omega U, omega V backslash U, A equals KV, omega UV, omega V backslash U, A. In plain terms, after fixing V, changing U doesn't change anymore. This happens when V mediates the effect of U, or when intervening on V changes the environment so that U no longer matters. This is not conditional independence, it's interventional dependence. And it reveals hidden structure. Some interventions can block others. Quantifying causal effects, from existence to strength. Now that we know if a causal effect exists, we ask, how strong is it? We introduce two measures. #1, mean effect score. For an event A, define SF do UQ A equals FP do UQ A minus FP. Here, F is a scale function, a user-defined weighting function that determines how we value changes in probability. If F is linear F, X equals X minus 1, 2, we get the raw difference, P do minus P. But if rare events matter more, say, changing probability from 0.001 to 0.01, we want a function with high slope near 0 and 1. Enter F2x equals sin 2x minus 1, 2, / sin 1. This function is symmetric around 1, 2, flat near 0.5, low sensitivity to changes in the middle, and steep near 0 and 1, perfect for emphasizing rare or near certain events. Back to our example. Buying insurance reduces P, pay equals 1,000, from 0.625% to 0%. With F2, the effect score is approximately minus 0.00675, negative, indicating reduction, and larger in magnitude than the raw difference. Why? Because the relative change from 0.00625 to 0 is massive, so F2 amplifies it. Similarly, not buying insurance increases the risk, score approximately plus 0.00942, showing a stronger positive effect. #2, maximum effect score. Instead of averaging over interventions, we ask, which outcome omega leads to the largest change in probability? Define omega max equals argmax omega b, f ku omega a minus f p a. Then the maximum effect score is f ku omega max a minus f p a. This identifies the most extreme causal influence, useful for detecting adversarial prompts or sensitive configurations. Causal effects on σ-algebras, beyond single events. So far, we've looked at events. But often, we care about entire distributions. For example, does buying insurance change the distribution of payments? Let f equals sigma, pay, the σ-algebra generated by the payment variable. We now define mean effect score on σ-algebras, using a difference measure df between two distributions. SDF equals df do uqp. df can be anything. Difference in means, variances, quantiles, or even infinite dimensional embeddings like kernel mean embeddings. Let's see what happens when we intervene on insurance. Mean effect score. Buying insurance increases expected payment by 8.45 CHF. You pay 30 for insurance, but avoid 1,000 CHF with high probability. Variance effect score. The variance drops by over 6,200. Why? Because the risk of a 1,000 CHF payment vanishes. So the causal effect isn't just about average cost, it's about risk reduction. And this is only visible when we look at the full distribution. ## recovering classical measures. Here's the beauty, all standard treatment effects are special cases. 8 average treatment effect, set f equals sigma y, df equals difference in means. Then SDF equals e minus e. Kate conditional 8, condition on x, same setup. DTE, distributional treatment effect. Use df equals Wasserstein distance, KL divergence, or kernel embedding. This shows the framework isn't just abstract, it generalizes and unifies existing theory. ## why this matters now. In language models, pixels, or complex systems, raw variables like tokens or pixels don't carry semantic meaning. But events do. The text is about politics. The image contains a cat. The model generates a harmful response. We can now ask which prompts cause this. How strong is the effect? Does it depend on context? And because the framework is measure-theoretic, it works for continuous, discrete, or hybrid spaces, perfect for deep learning. ## final thoughts. This paper shifts causality from variables to events, from binary questions to quantified strength, and from deterministic models to probabilistic, fine-grained reasoning. It draws a direct parallel to how independence was developed in probability theory. Start with events, then generalize. And just as we use correlation, mutual information, and divergences to measure dependence, we now have tools to measure causal strength. This is not just theory, it's a new language for understanding AI, medicine, policy, and the world. So the next time you ask, why did the model say that? You won't just say, the prompt caused it. You'll say, the event prompt contains right in a conservative tone, has a dormant causal effect on the event output, is politically conservative, but only when conditioned on the context of prior political content. And the maximum effect score reveals that this intervention increases the probability of that event by over 90%. That's causality at the right granularity.